100 billion galaxies containing billions of stars, clouds of gas, dust particles, planets, moons, and other cosmic debris make up only a small portion, less than 5%, of the total universe. NASA, on its website, informs us that 95% of the universe is actually composed of invisible matter and energy, consisting of 27% dark matter and 68% dark energy, two mysterious components that scientists continue to study to this day. So, what exactly are dark matter and dark energy? How can scientists detect something that cannot be seen and claim that it forms and influences our universe? To answer these questions, let us explore the mystery of this cosmic darkness. Everything in the universe that we can observe, such as galaxies, stars, planets, living beings, and all other objects, is made up of protons, neutrons, and electrons that combine to form atoms. All of these observable components are referred to in cosmology as normal matter, also known as baryonic matter. This normal matter accounts for only about 5% of the universe, which to us already seems unimaginably vast. In reality, however, normal matter is merely the smallest part of the universe's overall mystery. For hundreds of years, humans have studied the universe, until scientists eventually realized that something was wrong, something that should have been impossible. Yet, in the universe we inhabit, this impossibility truly occurs. The impossibility in question is the rotation of galaxies at extremely high speeds. Based on the gravitational force produced by normal matter alone, galaxies should not be able to hold themselves together. They should have long ago flown apart or collided with one another. What scientists observed was truly irrational and impossible from a conventional scientific perspective. They conducted further research to find an explanation, which led to the understanding that there must be something we cannot see, something that exerts influence, stretching the universe and binding matter together in unexpected ways. To simplify this, let us consider it from the perspective of standard physics. Imagine stars located at the outer edges of a rotating spiral galaxy. According to classical expectations, these stars should move much more slowly than those near the galactic center, since gravitational influence weakens with distance. However, observations reveal something strange. These stars orbit at nearly the same speed as those closer to the center, seemingly unaffected by their position within the galaxy. This result is indeed puzzling, one might even call it impossible. But it becomes understandable if we assume that the stars at the edges of galaxies experience the gravitational effects of unseen matter, which scientists call dark matter. The existence of dark matter was only discovered by astronomers in the 20th century. In the 1930s, a Swiss astronomer named Fritz Zwicky first coined the term dark matter while studying the Coma cluster, which contains more than 1,000 galaxies. The speed at which galaxies move within a galaxy cluster generally depends on the total mass and size of the cluster. However, Zwicky observed that the galaxies in the Coma cluster were moving much faster than could be explained by the amount of visible matter alone. Later observations developed further, and the existence of dark matter was confirmed by an American astronomer named Vera Rubin. In the 1970s, while studying how galaxies rotate, Vera and her colleagues discovered that galaxies likely contain unseen mass made of dark matter. Scientists today believe that dark matter exists in vast, web-like structures stretching across the universe, pulling most normal matter along with it. Even with increasingly advanced observational technology, we are still unable to observe dark matter directly. Dark matter does not emit or absorb light or electromagnetic radiation, making it completely invisible to telescopes and extremely difficult to detect with current scientific instruments. Scientists estimate that dark matter makes up about 27% of the total mass and energy of the universe. They also believe that dark matter exists because of its gravitational effects. Like normal matter, dark matter occupies space and has mass. Unfortunately, due to limitations in current research tools, scientists are still unable to determine what dark matter is actually made of. Existing theories suggest that dark matter consists of several types of unidentified particles that rarely interact with normal matter, making them difficult to detect. One important clue about dark matter is that it can cause optical illusions or bend light from distant objects behind it. This phenomenon is known as gravitational lensing and helps astronomers measure the mass of dark matter in galaxy clusters. A simple analogy is like looking at a playground from a distance. Imagine a long, slippery slide in the playground. When light from a street lamp behind the playground hits the smooth surface of the slide, the light bends and forms strange, magnified patterns. In space, a similar effect occurs due to dark matter. There are massive celestial objects we cannot see, dark matter itself. When light from distant galaxies passes through dark matter, it bends and becomes distorted, much like street light bending when it hits a slippery slide. As a result, the images of galaxies we observe may not represent their true shapes but have been altered by the influence of dark matter. In short, strange images of galaxies with rings and arcs of light can occur because of massive, invisible objects bending light from more distant galaxies. In addition, dark matter can be detected through small fluctuations in the cosmic microwave background radiation, the leftover light from the Big Bang. By studying this radiation, scientists can observe how matter has been distributed throughout the universe since its earliest moments. The distribution does not match what we would expect if only visible matter existed. Something is missing: dark matter. To this day, the true nature of dark matter remains unknown, though many theories attempt to explain it. One of the most popular is the exotic particle theory, which suggests that dark matter may consist of strange, unfamiliar particles unlike those we encounter in everyday life. These particles do not interact with light but still exert gravitational force. Another popular theory involves modifications to gravity, proposing that our current understanding of gravity may be incomplete and that a different form of gravity might operate on very large scales, such as within galaxies. In the effort to uncover the truth about how dark matter is formed, scientists are conducting various studies. One major focus is the search for dark matter particles using the Large Hadron Collider, LHC, a massive machine designed to collide subatomic particles at speeds close to the speed of light. The LHC was originally built to study fundamental particles that make up the universe and to test theories of physics. It consists of a 27-kilometer circular tunnel located underground along the border between Switzerland and France, lined with thousands of powerful superconducting magnets that accelerate and guide particles inside the tunnel. In addition to the LHC, scientists also study light from distant galaxies using the most advanced telescopes to search for clues about the existence of dark matter. If any of these efforts succeed, we will gain a much deeper understanding of the mystery of dark matter, the composition of the universe, and especially how galaxies are able to form and remain bound together. Although dark matter is already mysterious, dark energy is even more so. In the 1920s, astronomers, including Edwin Hubble, discovered that galaxies appear to be moving away from Earth, indicating that the universe is expanding. The farther away a galaxy is, the faster it appears to recede. This fact shows that the rate of the universe's expansion is not constant but is accelerating. This means there must be a force that counteracts gravity and pushes the universe to expand faster. This force is what we call dark energy. If dark matter is the fuel that allows galaxies to form and cluster together, then dark energy is the accelerator that drives the universe to expand at an ever-increasing rate. Dark energy is very different from matter, whether normal matter or dark matter. Matter has mass and occupies space, whereas dark energy fills all of space and has no mass. If dark matter pulls celestial objects toward one another, dark energy pushes them apart. What dark energy shares with dark matter, aside from both being invisible, is that its origin remains a mystery. Several theories have been proposed by scientists to explain the source of dark energy. One of them is the cosmological constant, a concept introduced by Albert Einstein to describe a static universe. However, after the discovery that the universe is actually expanding, Einstein referred to this concept as his greatest mistake. In simpler terms, the cosmological constant represents energy inherent in empty space, or the vacuum. Imagine empty space as an empty city. According to quantum theory, even the most perfect empty city still experiences constant energy fluctuations. This energy is known as vacuum energy, and the cosmological constant describes its energy density. When associated with dark energy, the cosmological constant offers the simplest explanation, as it describes a repulsive force that opposes gravity and causes the universe to expand at an accelerating rate. However, despite its simplicity, this explanation has unresolved problems. The measured value of the cosmological constant is extremely small compared to the value predicted by quantum theory, a discrepancy known as the fine-tuning problem. In addition, the nature of vacuum energy and how it interacts with gravity are still not fully understood. Because of these issues, other theories have been proposed, such as quintessence, which has dynamic properties and can change over time and space. This means that the effect of quintessence on the expansion of the universe may vary over time. Quintessence is also described as a scalar field, similar to the Higgs field that gives mass to particles. This scalar field has a complex energy potential that allows its energy density to change over time. This theory was proposed because the quintessence model offers greater flexibility in explaining cosmological observational data compared to the cosmological constant model. Some observational data even suggest that the rate of the universe's expansion may not always be constant. Therefore, the quintessence model can explain a more complex evolution of dark energy, such as why the universe experiences accelerated expansion, and it can also address the fine-tuning problem faced by the cosmological constant model. In addition, quintessence can be linked to particle physics theories, such as superstring theory or quantum field theory. Unfortunately, the quintessence model also faces challenges in its application, mainly because it is more complex and less tested, as it does not yet have strong observational support like the cosmological constant model. There is still another theory proposed as an attempt to understand the origin of dark energy, namely modifications of gravitational theory that are used to explain the accelerated expansion of the universe without involving dark energy. However, this theory is less popular compared to the two previous theories. In 1998, two independent research groups announced that they had measured cosmic expansion with higher precision and found that the expansion was accelerating. Now, how do we know that dark energy exists? Astronomers have measured the expansion of the universe using explosions of white dwarfs, which are the remnants of stellar cores that have exhausted their nuclear fuel and collapsed into extremely dense objects. These explosions are also known as supernovae. They are called standard candles because their peak brightness is very consistent, making them useful for measuring the distances of galaxies. This led to the discovery of dark energy in 1998, when distant galaxies showed that the universe is not only expanding but doing so at an accelerating rate, a phenomenon that can only be explained by the existence of dark energy. These supernovae occur when a white dwarf star slowly pulls material from its companion star. When the white dwarf's mass reaches the Chandrasekhar limit, or about 1.4 times the mass of the Sun, the internal pressure can no longer withstand gravity, triggering an uncontrollable nuclear fusion reaction and causing a massive explosion known as a supernova. In addition to supernova explosions, dark energy is also inferred through the cosmic microwave background, CMB, which is the leftover radiation from the Big Bang. By studying fluctuations in the CMB, scientists can calculate the amount of matter and dark energy in the universe. Baryon acoustic oscillations can also be used to detect dark energy by analyzing sound waves that formed in the early universe. By studying these waves, we can determine the composition of the universe. So far, the discovery of dark energy has challenged humanity's understanding of gravity and the universe. Dark energy is believed to determine the ultimate fate of the universe. If dark energy continues to dominate, the universe will keep expanding forever, becoming increasingly cold, empty, and desolate. Our universe holds mysteries far darker than the darkest night. Dark matter and dark energy, two mysterious components that dominate the cosmos, have long puzzled scientists. Although we know of their existence through their strong gravitational effects, their fundamental nature remains unknown. Current research involving underground detectors, space telescopes, and particle accelerators aims to lift the veil on these mysteries. However, understanding the fundamental nature of dark matter and dark energy is a major challenge that could transform how we view the universe as a whole. Further discoveries in dark matter and dark energy research will not only address fundamental questions about the universe, but may also open the door to new discoveries in physics. By continuing to explore the cosmic darkness, scientists hope to find clues that reveal the true nature of dark matter and dark energy. Such discoveries have the potential to revolutionize our understanding of the universe and lead us toward a deeper comprehension of the origins and ultimate fate of the cosmos. Dark matter and dark energy are two mysterious components that dominate the universe. Although we do not yet fully understand their fundamental properties, intensive research is underway to uncover these mysteries. Using a wide range of tools and techniques, scientists continue striving to solve a puzzle that has long been perplexing. Discoveries in this field will not only answer fundamental questions about the universe, but also potentially open the door to new physics and change the way we perceive the world. All efforts to uncover the mysteries of dark matter and dark energy have shown us how little we actually know about the universe. Despite the great progress achieved in science, the universe still holds many secrets. Dark matter and dark energy are just two small examples demonstrating that the universe is far larger and more complex than we previously imagined. The matter we see and experience every day turns out to be only a small fraction of the universe's total mass and energy. These discoveries also raise questions about the possibility of life elsewhere in the universe. If most of the universe consists of matter and energy very different from what we know, then the possibility of very different forms of life also becomes conceivable. The discovery of dark matter and dark energy also forces us to reconsider our position in the universe. If we are only a small part of a vast and complex cosmos, then we may need to revise our view of humanity's importance in the universe.